Hi, this is Patel. In this lecture, we are going to learn about the thermal stress applications in the composite bars. Now, whenever you solve this type of examples, then you will see that there are two types of bar which is available to solve in our syllabus. First of all, the first one is the composite bar and the second one is the compound bar. So, in this lecture, we are going to look at the composite bar first. So first of all, we will understand how these composite bars can be identified in our examination. Based on the diagram, we are going to identify the composite bars in our question paper. After that, there are multiple steps in order to solve this type of examples. And I will show you those steps so that you guys can solve this type of examples easily in your examinations. So let's get started with the first slide. And first slide is nothing but the basic concept to solve the composite bar. In your screen, you can see that the composite bar is made up of the two different material. The first material is shown as the steel material and the second one is the copper material. Now, it is but natural that both the material are different from each other, and that is why it is their own property to expand according to the temperature difference. So for the same temperature difference, steel material will expand only up to this point and copper material will expand up to this point. So delta L or expansion due to temperature change for both the material is different. Now in order to find out the combined effect of the composite bar or the entire bar, you need to understand that which material is going to get compressed and which material is going to get elongated. So how we are going to understand that both the materials are connected over here on the edges, or we can say that on their contact surface both the materials are connected together. So whenever first the copper material tries to elongate or expand more than the steel material, it will also try to pull steel material along with it. So as you can see in this diagram, we have shown the arrow in the upside direction, which indicates that the steel material is going to get elongated or it is going to experience the tensile force due to the pull force of the copper material. Now the opposite effect will appear in the copper material. What will happen? Copper will try to elongate further as compared to steel, but steel is not willing to go further. So steel will pull down the copper material, and that's why the copper material will face the compressive force as shown in this figure like this. So this figure shows the downward arrow which indicates the compressive force, which indicates the compressive stress in the copper material. So this is the key to identify the nature of the stress in each of the material. So we can say that the material which is trying to expand more is going to experience the compressive stress, and the material which is trying to expand less is going to experience the tensile stress. Which material will try to expand more? The material which is having the alpha value, which is nothing but the coefficient of thermal expansion. The material which is having the alpha value more than the other material will experience more expansion as compared to other material. So this thing you have to keep in your mind while solving the example. So let's get started with the nomenclature that we have used in this particular concept. That the sigma 1 is the stress in the copper material, epsilon 1 is the strain in the copper material, alpha 1 is the coefficient of thermal expansion or linear expansion for a copper material, and A1 is the cross section area of the copper bar. Cross section area means if you cut the copper material and if you look from the cross section point of view, or we can say that from the top, then the shape of the area or the amount of area will be known as the cross-section area of the copper material. Similarly, we can identify this notation with the suffix 2 for the another material, that is in our case it is steel material. Now we are going to understand that the epsilon is the actual strain of the composite bar, means the entire bar will face epsilon amount of strain into the material, or the overall bar. So which concept are we going to use to solve this type of example? The first concept is the compressive force in the copper is equal to tensile force in the steel. That is also known as the action and reaction equal and opposite. So the amount of compressive force that will be applied on the copper will be equal to the tensile force applied on the steel. So this is how we are going to find out our step number 1. So step number 1 is nothing but the same amount of the forces but of equal nature in both the material. So for the first material, that is copper, the force can be written as sigma 1 into A1, and for the second material, that is steel, the force can be written as sigma 2 A2. So it is clear that sigma 1 A1 equals to sigma 2 A2. This is our equation number 1. We know the value of area, or we can say that the cross section area. So cross section area value will be inserted into this equation, and due to this we will get the relation between sigma 1 and sigma 2. Further, we will go with another equation. What is that equation? That the strain in the copper is written as epsilon 1. So as you can see, strain in the copper epsilon 1 is the individual strain of the copper material only. So if we allow the strain in this particular free expansion, the amount of strain will be alpha 1 into T. That is based on the free expansion definition that we have learned in our previous lectures. But the epsilon is the actual amount of strain which is acting on the entire composite bar. So if we take the difference of free expansion and the actual expansion or actual strain, then we can get the strain which is causing the stress in the copper material. So epsilon 1 is the amount of strain which is causing the strain in the copper material. Now similarly, we are going to find out the strain in the steel material. So steel material can be calculated as epsilon minus alpha 2 into T. Why we have done this like this? Because we need to subtract the smaller value from the bigger value. So if you narrate from here, then you will find out that epsilon value will always be greater than alpha 2 into T, and epsilon value will be less than alpha 1 into T. That is why we will remember like this, that we will always subtract the smaller value from the bigger value. So alpha minus epsilon minus alpha 2 into T will give you the value of epsilon 2, which is nothing but the strain in the steel material. Now both the materials are combined together. That is why epsilon 1 plus epsilon 2 will give you the summation of above two equations. And if we simplify this equation, then we will see that this epsilon and this epsilon is getting cancelled out due to the positive and negative sign. So we are getting the final equation as epsilon 1 plus epsilon 2 equals to T into alpha 1 minus alpha 2. So these are the two different steps. The first number of step is this one, and the second step is this one. If you apply these two number of steps in any composite bar example, then you will get the answer of thermal stress definitely in any examination. So these are the basic steps that you need to remember before starting the examples. Now we are going to apply these steps into the example so that you guys can understand in practical. Let's get started with the first example. The given data of the example is shown on your screen. where you will see that the steel rod of 25 mm diameter is inserted inside the brass tube. So there are two different materials. The first one is the steel rod which is inserted into the brass tube. Now the brass tube is having the 25 mm internal diameter and 35 mm external diameter. So the tube is hollow. That is why it is but obvious that it contains two different diameters, inside diameter and outside diameter. So the inside diameter is the 25 mm, which is similar to the steel rod, and outside diameter is 35 mm. Now these two materials are connected rigidly at the end. Both the materials are connected rigidly at the end. So this is the basic condition of the composite bar. Both the materials should be connected together rigidly. If it is not given in your example data, then we have to assume that both the materials are connected together rigidly. Next, the assembly is heated by 30°C, which means that after assembling and connecting together both the material, we are increasing the temperature of the assembly by 30°C, which means that the delta T, or we can say that T value, is given directly as 30°. Find the value and nature of the stress developed in both the materials. So here steel and brass, two materials are given, and we need to calculate the nature and value of the stress which is being developed into those two materials. For that, they have also provided value of Young's modulus for steel material as 200 gigapascal and for brass material as 80 gigapascal. Alpha for both the material is given, and from the given data we can say that alpha of brass material is more than alpha of steel material. So it is but obvious that the brass material is going to experience the compressive nature of stress and steel material is going to experience tensile nature of stress. So this is our basic diagram which we have made through the description. So based on the description, we have shown here the rigid plates which is connecting both the material together. Inside that there is a steel rod, and outside of it there is a brass tube. So both the materials are shown with different notation. Now we are going to list out the given data. So first of all, the area of steel rod can be calculated using the pi by 4 d square formula, which will give you the answer of 490.87 mm square. If you want to calculate the area of brass, then brass tube will look like this from the side view, and we need to calculate the area of this ring only. And if you want to calculate the area of this ring, then what you are going to do? We are going to subtract the inner circle from the outer circle. So the equation will look like this: pi by 4 outer diameter square minus pi by 4 inner diameter square. So outer diameter is 35 mm square and inner diameter is 25 square. So it will give us the answer of the brass tube area, that is nothing but the 471.23 mm square. T value is given as a 30°C, which is nothing but the temperature base or temperature increase. Young's modulus is given as 200 gigapascal, which we need to convert into Newton per mm square by multiplying 10⁻⁵. Also, we have multiplied 10⁻⁵ to the Young's modulus of brass material. Alpha value is given as it is, and alpha S is the stress, sigma S is the stress in the steel material. Sigma B is the stress in the brass material, and we know that the alpha of the brass is greater than alpha of steel. That is why the brass tube will be subjected to compressive force and steel rod will be subjected to tensile force. So this will give us the nature of the stress that is being developed in both the materials. So this statement is compulsory in your examples. Now what? We are going to move forward in our steps. That first step is the amount of force is equal in both the material. So this is our step number 1, where sigma S into AS equals to sigma B into AB. Now what we are going to do, we are going to keep areas into one side and put the values of area like this. So this is our areas. If we simplify those area, then we will get the relation between the sigma s and sigma b. Now we are going to leave this equation as it is and we will move forward to the step number 2. And for step number 2, we need to calculate epsilon s and epsilon b first. So epsilon s is calculated by sigma s upon E into s. Now putting the value of E into s, we can get the epsilon s in terms of the sigma s. Again, similarly, we are going to calculate this epsilon b in terms of sigma b. Now, if you put both this value in our step number 2 we have discussed in our theoretical portion, and if we put all this value, then this will give us the equation like this. So this is our final equation after putting all the values into the step number 2. Now you will see that this equation contains only two unknowns, that is sigma b and sigma s. Now what we are going to do, we are going to apply this relation into the equation like this. So if we put this equation number 1 into our equation, then it will give us the only one unknown into entire equation, that is sigma b. If we take out sigma b common and simplify the rest of the equation, then we will be able to calculate the answer of sigma b as 10.40 Newton per mm square. We have already mentioned that sigma b is the stress of the brass material, and the brass material is facing compressive force. That's why the nature of the stress is compressive. If you put this value in the equation number 1, then you will be able to calculate the value of sigma s. Sigma s is nothing but the stress of the steel material, which is of the tensile nature. So this is how we calculate our example. All you need to do is to remember two number of steps that we use to calculate the example of composite bar subjected to thermal stresses. So this is the application of thermal stress in the composite bar. In the upcoming lecture, we are going to look at the applications further. Till then, we conclude our lecture over here. Thank you.